Chapter 22 is all about coordination chemistry. And coordination chemistry is chemistry of transition metals and compounds that they form in solution by forming new bonds with different molecules of ions. So anyway, because we're coming back to transition metals after perhaps a long time, the first thing we need to review is how to name transition metal ions. So if I have something like CuSO4, then we need to recognize that copper, being a transition metal, might have different charges, and so in order to tell the charge on the copper, we're going to have to look at its bonding partner. Here we have SO4 2-, and the copper needs to balance that 2- charge, so it would be Cu2+, and that means this compound is called copper 2 sulfate with that Roman numeral 2. I could make another compound here. If I have two coppers, then we'll have the SO4 2-, we'll have 2 times Cu1+. Each of the coppers will only carry a 1+ charge in order to counterbalance that sulfate ion. So this would be copper 1 sulfate. So not all transition metals are going to have the same charges available to them. Copper is typically in the 2+, but can be in the 1+. And anyway, we'll actually go over this a little bit more later. But the transition metals can take a variety of charges, and you need to use the Roman numeral to indicate exactly which charge you're talking about in a given compound. Okay, and that's 22.1, so I'm going to go ahead and group 22.2 together with 22.1. So the chemical properties of the transition metals depend on their electronic configuration, and in particular, the transition metals differ in the number of electrons in their d block. So you may recall, this is all the way back from chapter 8, that electrons are grouped according to what we call subshells: the s subshell, the p subshell, the d subshell, and the f subshell. So for transition metals, as you go across the periodic table, you're adding new electrons into the d subshell for the transition metals. They reside in what I call the d block of the periodic table, or everyone calls it the d block. Anyway, and so it's the electronic configuration of the d subshell itself that is going to be important for it's going to be important for the properties of transition metals. So let me hurry and advance to the next figure. Okay, so table 22.1 shows the electronic configurations for 3 rows in the D block. And most of them are what you might expect. So scandium has the argon core 4s2 3d1. Titanium has the 4s2 3d2. Vanadium has the 4s2 3d3. But chromium is going to upset your expectation here. It has just 1 electron in the 4s subshell and 5 electrons in the 3d subshell. And how we usually explain this is that a half-filled subshell is particularly stable. What you gain is that you no longer have to pair 2 electrons within the same orbital in the 4s subshell. And so that's the configuration for chromium. Manganese gets right back on track with 4s2 3d5. And anyway, going along, copper there has that same problem with only one electron in the 3s subshell and now 10 in the 3d subshell. So it has promoted an electron from its 4s to its 3d. And if we look at the next row, oops, went too far. If we look at row 5, then molybdenum and niobium do the same thing that chromium did before. Argon, I'm sorry, that's not argon, that's silver and palladium, elements 46 and 47, also do it. In fact, ruthenium and rhenium, almost half of the elements on row 5 are going to have some sort of funny business with the electrons in its 5s subshell being promoted to the 4d subshell. And then when you get to row 6, things settle down a little bit. Here you see there's only an exception to our expectations for platinum and gold, elements 78 and 79. And the fact that we have an F subshell is kind of an explanation for why you don't have quite as many exceptions on this row. But one thing we should remember is that let me go back to row 4. Okay, and let's consider the electronic configuration for, let's do nickel and nickel 2+ ion. So for nickel is already shown there. It's the 4s2 3d8. So for nickel 2+, you're going to have the argon core, and then it's lost 2 electrons, and all of the transition metals are going to lose their s electrons before they lose their d electrons. So for nickel, you'll have still all 8 electrons in the d subshell. What you will have lost is the 4s electrons. And copper 1+, for example, would also have the argon with now 3d, what is it, 9? Oh no, it'd be 3d10. I apologize. 3d10. And copper 2+ would be argon with the 3d9. Now finally we lose a d electron, and so this helps to explain why copper has a 1+ ion and a 2+ ion. Most transition metals will only have 2+ or greater because they will readily lose both of their s electrons together at the same time. Copper only had one s electron to begin with, and so the 1+ ion corresponds to emptying out its s subshell, and then the 2+ is just then going on to remove a d electron as well. And copper 3+ also does exist, although it's by far the least common, and that would have 3d8, right? So, hold on a sec. Let me get to the next figure. So table 22.2 I'm about to put up here. Table 22.2, you don't need to memorize this at all, but this kind of summarizes for the row 4 transition metals what charge states or oxidation states are common or uncommon or disallowed. And you'll notice that ones that are near the beginning or the end of the row have fewer charge states. So the ones at the beginning just don't have that many electrons to give up. Scandium only has 3 valence electrons, and so if you take away all 3 of those and form a 3+, well, then that's it. There are no more valence electrons to remove. And then ones near the end, like copper and zinc, well, having a completely filled subshell is particularly stable, and so it just takes a lot of energy to disrupt that stable configuration by removing an electron. Ones in the middle, like manganese here, manganese has 6 possible oxidation states, and that's because it's got a lot of room to reconfigure its electrons after you take some away. It's got plenty of electrons to give, and although we only see row 4 in this table, you would see similar trends for rows 5 and 6 of the transition metals as well. So like I said, you don't need to memorize this, but I think it really drives home the point that transition metals have complex oxidation numbers, and you shouldn't take for granted that they're going to be in any particular charge state. And again, we see clues that it's the electronic structure, the configurations of the d subshell electrons that govern what is stable and what is not in these transition metals. So the rest of this chapter is looking at 3 different periodic trends. We already talked about periodic trends, so the 3 that last year we did. So the 3 that we're going to look at are atomic radius, first ionization energy, and electronegativity. Okay, so the atomic radius, you may recall, is going to increase as you go down a column, and that makes sense because your atoms are getting bigger and bigger. Not only are they more massive, they have more weight, but they've got more shells of electrons. And so the atomic radius is going to increase down the periodic table. But surprisingly, it's actually going to decrease across the periodic table. And so the very biggest elements are in the lower left, and the very smallest elements are in the upper right. Okay, well, let's look at what we see in the transition metals. And again, give me a minute, I need to skip ahead to the right figure. Okay, so this is figure 22.2, and you see that for any given row, they have row 4 in red, row 5 in yellow, and row 6 in blue. Then this trend of getting smaller across a row seems to be consistent. Although if you were to put this in context, you would see that the contraction across the D subshell is pretty small compared to, say, the contraction across the P subshell with fewer electrons. And so we see the same trend, it's just sort of smaller. Sorry, I used a better word. No, I guess I didn't. Okay, the changes are smaller than expected. And then as you go down, the elements should get bigger. And we do see that for at least most of the elements, row 4 is the smallest, and row 5 is the middle, and row 6 is the greatest. But there's a good handful where row 5 and 6 have switched places. And that's because row 6 has an F block, and that F block is going to sort of lead to a greater amount of contraction than row 5, which doesn't have the F block. In other words, by the time you get to the first element in the 6th row, you've already added 14 extra protons and 14 poorly shielding electrons, and you're going to have a much greater effective nuclear charge that's going to contract the 6th row to be basically about the same size as the 5th row. And you know, they sort of dance around one another a little bit, but they're essentially about the same size. So that phenomenon is called lanthanoid contraction. Lanthanum is like the beginning of the F block on the 6th row. And so the lanthanoids are all of those elements in the F block of the 6th row, and it's their existence which leads to the contraction of the 6D transition metals. And so it's called lanthanoid contraction. You don't need to know that term, but that's what explains it. So next is first ionization energy. Okay, and the first ionization energy is going to increase as you go across a row, and that's because of the smaller radius and the higher Z effective charge are going to make it more difficult to remove an electron. And it's going to increase near the top of a column, and that's because of the smaller radius holding the electron closer to the nucleus. So you'd expect the highest ionization energies to be in the upper right corner and the lowest in the lower left corner. Let's see how the transition metals actually fare. Okay, and they certainly do follow that trend. So moving across a row, clearly we see the trend is for increasing ionization energies. And then 4 has a higher ionization energy than 5, so that makes sense. But again, period 6, because of all those lanthanoids, it's like effectively further to the right than periods 4 and 5 are. So period 6 upsets our expectation a little bit. It's the furthest down, and yet their ionization energies are the highest of those 3 rows. And then also you'll see some exceptions. So on period 4, you can see chromium and nickel and copper are sort of all a little bit lower than you would expect. Those are also the elements that are showing an exception to the rule for their electronic configurations. They are the ones which have a 1s electron that was promoted to the D subshell. And so that one remaining S electron is easier to remove than you would normally expect. And those same sorts of exceptions happen in period 5. You can see silver has a particularly low first ionization energy. Anyway, there are some exceptions because of that. Now, electronegativity is actually kind of an abstract thing. There are competing definitions of electronegativity, so it's not like something that you can measure and know the value of. It's actually calculated based on other measurements, and exactly what formula you use depends on what sort of electronegativity model you want to use. There are competing ideas. But anyway, electronegativity essentially means the atom's attraction toward electrons that are being shared in covalent bonds. So a highly electronegative atom is going to pull more than its fair share of electrons in covalent bonds toward itself and lead to a polar molecule. A very low electronegativity atom is going to be more free with sharing its electrons with its bonding partner. And of course, if you have a big difference in electronegativities, that leads to a strong bond dipole. Now, electronegativity also is going to increase as you go across a row. The highest values are at the top, and so elements like fluorine have highest electronegativities. Elements like cesium and rubidium have the lowest electronegativities. And let's see how the transition metals do. Okay, and you see here, you can kind of make the case that this follows the trend across a row. although it seems to peak halfway through and then bounce back downward. And then it's actually the exact opposite of what you would expect as far as going down a column. Well, there's some crossing points. The first couple of elements will follow the trend where the fourth row has the higher electronegativity than the fifth, and the fifth higher than the sixth. But very quickly they invert that order. And anyway, electronegativity, like I said, it depends on other things like the ionization energy and the electron affinity, for example. And because there are so many exceptions and strange things at play with both of those, it's like their errors are compounded in when you consider electronegativity. And so electronegativity is really kind of all over the place. There are quite a few exceptions to the rule that we would have expected. Anyway, bottom line is that the transition metals are complicated and they're unexpected. Each transition metal is kind of going to have its own character or personality based on all of the little underlying factors that control these periodic properties. They're a lot less predictable than main group elements, and that makes chemistry that deals with transition metals kind of fun and exciting. So that's it for section 22.2.